Welcome back to Computer Lessons.
Digital hardware remains vulnerable to internal and external interference that alters raw binary data during storage or transmission tasks. Microscopic bit flips occur when a transistor changes state without a software command due to electrical noise or cosmic radiation. These random events represent a constant threat to system stability and data integrity. Binary information travels as electrical pulses or magnetic charges that exist within a specific range of physical tolerance levels. Environmental heat or electromagnetic pulse events can push a 0 to a 1 or force a 1 to 0. Modern computer engineering requires robust detection and recovery systems to counter these inevitable hardware failures at the logic gate level. The simplest form of data verification is the parity check, which adds a single redundant bit to a block. In an even parity system, the extra bit ensures the total count of ones in the byte is even. This basic logic allows the hardware to identify that an error occurred during the transmission of that segment. However, parity checks possess a major architectural flaw because they can only detect an odd number of simultaneous bit changes. If two bits flip at the same time, the total count remains even and the error stays hidden. This limitation forces engineers to utilize more complex and layered verification strategies for mission-critical systems. Checksums provide a higher tier of verification by summing the numerical values of a data packet before the transmission. The receiver performs the same addition and compares the result to the value stored in the packet header. If the numbers do not match exactly, the hardware knows the data packet contains some form of corruption. Cyclic Redundancy Check, or CRC, uses polynomial division to generate a unique digital fingerprint for a block of raw data. This method is far more powerful than a simple checksum because it detects a wider range of burst errors. Network protocols like Ethernet and storage systems like SATA rely on CRC for hardware-level error detection. Detecting an error is only the first half of the problem for a modern high-speed computer processing unit. Forward error. Correction allows a system to fix corrupted data without requesting a retransmission of the original signal. This capability is vital for deep space communication and high-speed wireless networks where latency is high. Richard Hamming revolutionized this field by creating the first error-correcting code that could both find and repair errors. Hamming codes use specific redundant bit positions to create a logical grid of checks across the entire data word. This structure allows the processor to determine the exact bit that flipped during the storage process. The Hamming distance is a core metric that defines the number of bit positions in which two binary strings differ. Increasing the distance between valid code words allows the hardware to correct more errors per block of data. This formal logic ensures that even if several bits fail, the true information remains recoverable for the OS. Server environments require extreme reliability and utilize specialized hardware known as error correction code, or ECC memory modules. Standard RAM lacks the extra bit lanes required to store the redundant parity information needed for live repair. ECC RAM detects and fixes single-bit errors in real time to prevent sudden system crashes or reboots. A single-bit error in the kernel memory space can cause a catastrophic failure of the entire operating system. ECC hardware provides an invisible layer of protection that identifies these flaws before the CPU processes the wrong value. This is the primary reason why professional workstations and data centers invest in more expensive memory. Advanced systems utilize SECDED logic, which stands for single error correction and double error detection during active tasks. This means the hardware can fix one bit flip and stop the system if two bits flip at once. This fail-safe prevents the computer from processing corrupted data that it cannot fix with absolute certainty. Burst errors occur when a physical event like a scratch on a disk causes a sequence of bits to fail. Standard Hamming codes struggle with these groups because the errors are concentrated in a single location in the stream. To solve this, engineers use interleaving to spread the bits of a single file across different blocks. Reed-Solomon codes represent a masterclass in information theory and form the basis of modern storage and communication. These codes treat data as points on a complex geometric curve instead of simple bits in a line. This allows the system to recover massive chunks of missing data from just a small fragment of info. You find Reed-Solomon codes in every QR code on a wall and every compact disc in a player. You can scratch a portion of a QR code and the camera can still read the original message. The mathematical redundancy built into the image allows the software to reconstruct the missing visual data points. Modern SSD controllers use low-density parity check, or LDPC codes, to manage the physical wear of flash cells. As flash memory ages, the chance of a bit flip increases due to the degradation of the oxide layer. LDPC codes use iterative algorithms to extract the correct signal from the background electrical noise of the drive. In satellite and space communication, the signal-to-noise ratio is often so low that data becomes unrecognizable. NASA uses turbo codes and polar codes to squeeze every possible bit of information out of a weak signal. These methods approach the theoretical Shannon limit, which is the maximum speed possible for a specific channel. Signal mapping techniques like gray coding ensure that a single bit flip during transmission causes the smallest possible error. In this system, adjacent symbols only differ by 1 bit in their binary representation in the hardware. This minimizes the impact of noise on the final result interpreted by the receiving computer system. High-speed data buses like PCIe5 and DDR5 introduce so much interference that error correction is mandatory. At these frequencies, the wires behave like antennas that pick up stray signals from the rest of the board. Without internal error management, these high-speed interfaces would produce nothing but garbage data and system errors. Software layer verification acts as the final guard against silent bit rot in long-term archival storage. Systems like ZFS and BTRFS use cryptographic hashes to ensure that the file on disk is identical to the original. If the hash does not match, the file system uses a redundant copy to fix the disk. RAID systems provide error correction at the drive level by using dedicated parity disks to store recovery information. In a RAID 5 array, the system can reconstruct the entire contents of a failed drive using math. This ensures that companies can lose a physical hard drive without losing a single bit of customer data. The trade-off for this extreme reliability is the cost of storage overhead and increased processing power requirements. Storing redundant data means less space is available for the actual user files and applications on the drive. However, the cost of losing critical data far outweighs the expense of adding a few extra parity bits. In real-time video streaming, some data loss is acceptable to maintain a smooth playback for the user. The codec might ignore a few bit flips in a single frame to avoid the lag of a retransmission. This shows that the level of error correction depends on the specific needs of the software application. Artificial intelligence is now being used to design new types of error-correcting codes for neural network hardware. These systems learn the patterns of noise in a specific circuit and create a custom protection layer. This innovation will allow for even smaller and more energy-efficient processors in the future tech. Every bit of information you send across the planet is protected by these layers of invisible digital armor. The battle between raw physical noise and structured binary logic is a core part of computer science. Engineering this certainty out of chaos is what makes modern global communication and storage a reality. Without these protocols, your computer would be a random noise generator rather than a tool for logical computation. The precision of the hardware is a direct result of our ability to find and fix its flaws. This technical foundation is what allows for the absolute trust we place in our digital systems today. In our next technical lesson, we will explore the world of character encoding from ASCII to the massive Unicode standard. We will explain how computers handle the thousands of different languages and symbols used by modern human civilization. This will show how numbers become the text you read on every screen in the world.
The engineering of error correction proves that even in a world of random cosmic interference, we can find truth. Our digital world is built on the hope that if something breaks, we have the math to fix it. Do you find the idea of random cosmic rays flipping your bits more frightening or fascinating for tech? If you found this explanation helpful, please hit the like button and subscribe to Computer Lessons. Don't forget to click the bell icon so you don't miss our next class. Thanks for watching and keep learning.